My name is Alex, and this is Unseen Systems, where we cut open the machines running quietly all around us. Here is today's question. You have heard that an electric car battery can catch fire, but the far more interesting story is everything the pack is doing every second to keep that from happening. So what is it actually fighting? It is fighting temperature. A lithium cell is only healthy inside a narrow band, very roughly 15 to 35 degrees Celsius. And here is the catch, it fails at both ends. Charge it when it is too cold and metal lithium plates onto the anode, permanent damage. Run it too hot, above about 45 degrees, and it ages fast. Cycle a pack at 45 instead of 25, and you can roughly halve its life. So follow the pack in cross-section. The exact chemistry and the exact numbers shift from car to car, but the rule underneath never changes. Most of what you are looking at is not storage, it is plumbing. Pressed against the cells sits a cold plate, a thin metal plate threaded with channels, carrying a water-glycol coolant. Its only job is to move heat. Under a hard drive or a fast charge, the coolant pulls heat out of the cells and carries it away to a radiator that dumps it to the air, or to a chiller tied straight into the car's air conditioning loop when it needs maximum cooling. A pump keeps it all circulating. That is the cooling half of the story. And here is the reframe. That loop is not a comfort feature. The cells genuinely cannot survive the temperatures they create under load, so the plumbing is life support. Kept low, the coolant is also a poor conductor of electricity, on purpose. If it ever leaks onto the high voltage gear, it should not hand the pack a shortcut. Safety folded into the cooling. Now watch the same loop run backward. Through a heater, increasingly a heat pump, the exact same plumbing warms the pack in the cold and warms it before a charge. One set of pipes, both directions. It cools the cells when they are too hot and heats them when they are too cold. Which sounds backward until you see why. Fast charging itself makes heat, push big current through the cell's resistance, and the waste heat climbs with the square of the current, double the rate, and you roughly quadruple the heat. And a cold pack cannot take that current safely, force it, and you plate lithium all over again. So the car does the thing that sounds upside down. It warms the battery first, into an ideal charging window. On a cold day, a preconditioned pack can jump from 20 or 50 kilowatts to well over 100. It heats the cells in order to charge them faster. So the whole pack is a temperature control machine wrapped around a chemistry that hates the temperatures it creates. But here is the part that makes a battery different from every other part of the car. A motor's worst case is that it simply breaks. A cell's worst case is that it ignites, and you cannot make that impossible. You can only make it slow, contained, and survivable. It begins with a single cell shorting on the inside, from a defect, from damage, from a metal whisker piercing the separator. Suddenly, energy dumps into one spot faster than it can escape. Heat generation outruns heat removal, and a chain of reactions starts feeding itself. This is thermal runaway. Watch it climb. Around 90 to 120 degrees, the cell's thin protective layer, the film that keeps the anode calm, breaks down, exposing reactive material underneath. The cell is now generating its own heat. Near 135 to 166 degrees, the separator, the whisper-thin sheet holding the two electrodes apart, melts. They touch directly. That is a full internal short, and the resistive heating spikes hard. The climb steepens. And now the beat that changes everything. Somewhere past 150 degrees for a common NMC cell, the cathode itself starts to break down and release its own oxygen. Read that again. The cell is now supplying its own oxidizer from the inside. The fire no longer needs air from the room, which is exactly why you cannot smother it, and why it can reignite. A tougher LFP chemistry holds out far longer, past 250 degrees, more stable but not fireproof.
All three of the crash-damaged batteries reignited after firefighters extinguished the vehicle fires.
Past 200 degrees, the cell vents burning gas in hot jets, and the whole thing self-sustains. Heating rates can reach tens of degrees every second. One cell is now a small torch, and it is sitting shoulder to shoulder with hundreds of its neighbors. So if you cannot stop one cell from failing, you change the goal. You stop it from taking the others. The pack gets compartmentalized like a ship. Bulkheads do not repair a breach, They keep one flooded compartment from sinking the whole vessel. Same idea in aluminium and aerogel. Because without those bulkheads, look what happens. The first cell goes into runaway, its heat and its jet of flame hit the cell beside it, and that one lets go too. A wave crosses the entire pack, cell by cell. That is the nightmare the design has to prevent. So between the cells sit thin barriers of aerogel or mica materials that barely conduct heat and shrug off 1,000 degrees. Some are intumescent. They swell into an insulating char the instant they are hit, and the vented gas gets routed along deliberate paths out of the pack, instead of pooling and igniting between cells. The failure gets walled off at one cell. And the rulebook has now caught up with that philosophy. China's battery standard used to ask only for a 5-minute warning, enough time for people to get out before any fire reached them. The revised 2025 version threw the compromise out. After engineers deliberately drive a single cell into runaway, the pack must produce no fire and no explosion for a full 2 hours, and no smoke may reach the cabin at all.
No fire, no explosion.
How much rides on all of this? Look at the Chevrolet Bolt. Investigators found 2 rare defects sitting in the very same cell, a torn anode tab and a folded separator, which together could let the electrodes touch and start exactly the chain we just traced. What began as 110,000 cars grew until nearly every Bolt ever built was recalled, about 141,000 of them, with at least 13 fires linked. GM told owners to charge only to 90% and park outdoors.
A torn anode tab and folded separator within the battery modules.
Now let us be fair about the risk soberly both ways. By one widely cited analysis, an electric car is far less likely to catch fire than a gasoline one, on the order of tens of fires per 100,000 cars, against well over 1,000 for gas. That figure is contested, so hold it loosely. But when an EV fire does happen, it is harder to put out, because, as we saw, the cell brought its own oxygen. Crews can pour tens of thousands of gallons of water on one, and it can still reignite hours later, from the energy left stranded in damaged cells. So what have we really been looking at under all that plumbing? Because the interesting thing about an EV battery is not that it stores a lot of energy. It is that most of the pack is not storage at all. It is a temperature system and a set of fire breaks, because the cells cannot survive the heat they make, and one of them someday will fail. The pack is a box built around that admission. So keep just one line and let the rest go. An EV battery spends almost all of its engineering not on holding charge, but on holding temperature, and on making sure that when a single cell finally lets go, it stays a single cell. So here is the real shape of the thing. An EV is not a big battery on wheels. It is a climate control system with cells riding along inside it. Picture your car on a freezing morning, quietly warming its own battery before it will take a fast charge, then watch the kilowatts climb as it does. That is the whole system, holding the cells inside their window. That's Unseen Systems. Systems fans, see you at the next one.